Welcome back. In this chapter, we're going to talk about inference on two samples. So in the previous chapter, we introduced hypothesis testing, and we did hypothesis testing on three different parameters, that being the proportion, the mean, and the standard deviation. Now in this chapter, we're going to deal with parameters from two different populations, okay? And we're going to see how they compare to each other. In some cases, these parameters are equal to each other. One might be greater than the other, one might be less than another. We're going to deal with all those types of claims in this chapter. Now, just like the previous chapter, we dealt with the proportion, mean, and standard deviation. Now, this chapter will rhyme with the previous chapter. But we're going to introduce at least one more section in here dealing with dependent samples. So let's start with revisiting what independent and dependent mean. A sampling method is independent when individuals selected from one sample do not dictate which individuals are to be in the second sample. And a sampling method would be considered dependent when individuals selected to be in one sample are used to determine the individuals in the second sample. Dependent samples are often referred to as matched pairs. We're going to have an entire section just on that. And that might sound complicated, but it's actually very easy. It's something that we've actually already done before in a way. And in these situations, it's possible for an individual to be matched with him or herself. For example, if you're dealing with maybe like a weight loss program, you're trying to find the effectiveness of some sort of diet, and you measure somebody's weight today, and we're going to measure this individual's weight in the future. And these are called matched pairs because one value from the before sample is matched up with a value in the future sample because it is the same individual. Again, we'll have a whole section to deal with that. But in this section, we are going to start talking about two population proportions. The next one will be two population means. The following would be matched pairs, and then finally two population standard deviations. The objectives here are to distinguish between independent and dependent sampling, test hypotheses regarding two proportions from independent samples, construct and interpret confidence intervals for the difference between two population proportions. And I did mention before that you can do hypothesis testing using the p-value method, which we've done in the previous chapter, which is the same steps are going to follow in this chapter, the same 6 steps. It'll get repeated over and over. Okay, but you can also do hypothesis testing using a confidence interval method, which we'll describe in just a moment. Okay, testing claims regarding two population proportions. In the test of two proportions, we have two values for each variable, one for each of the two samples. Two population proportions, P1, P2, and two sample sizes, N1, N2, and then two numbers with that certain characteristic. Let's say, for example, I'm trying to see if there's a difference between the pass rate for, let's say, a class that I teach traditionally, where people are face-to-face, or one that it's online, okay? So you might make a claim that there is no difference, or one is better than the other. Then you would have to actually get samples, right? You get your sample size from each class. Right? You have your first population, population 1, population 2. You would have to get sample size from each one. We'll call this N1, N2. Not both classes are exactly the same size. Probably they are, but most likely not. And then you have X1, those who pass in this first class, and those who pass in the second class. And if we come up with a sample proportion, which is P hat, we can call that P1 hat, X1 over N1. Over here, P2 hat would be X2 over N2. Now, when dealing with the null hypothesis, again, the null hypothesis is always a status quo statement, right? In this case, the status quo statement would be that these proportions are exactly the same, right? We would say something like P1 is equal to P2, right? Until, of course, we have evidence to suggest otherwise. If P1 equals P2, that is the exact same thing as saying P1 minus P2 is 0, meaning there is no difference. No difference. Now, if there is 0 difference, that means P1 is equal to P2. So overall, we can just say that they're the same proportion. We'll just call that P. And what we get to do for our best guess at this value of P would be what's called a pooled estimate for P, which would be those who have the characteristic from both populations that we're interested over the total sample sizes, right? So basically, in my example, all those who passed over all those who were taking these courses. So that's what's called a pooled proportion. Now, we're not going to really use this formula too much, but it is used in the test statistic, and we'll see that pretty soon. So let's just go right into the 6 steps. Requirements for testing a hypothesis regarding the difference between 2 population proportions. Okay. Of course, there's always conditions that need to be met before you can attempt this, right? And for proportions, it's always a matter to see if we can assume a normal approximation. All right. So samples are independently obtained using simple random sampling. Now we have to pass this NP times 1 minus P for both samples. Also, each sample does have to be less than 5% of the population size, respectively. And how does step 1 look like? Well, step 1 is always a hypothesis statement. Null hypothesis always has equality. In this case, it would be that P1 is equal to P2. A two-tailed test would be not equal to. A left-tailed test would be less than. A right-tailed test would be greater than, just like usual. Step 2 is just identifying that level of significance, alpha. The test set in step 3. Well, again, we're dealing with proportions, so we deal with a z-score. What we have here is we always have a difference between our data and what we have in the null hypothesis. Okay, so this comes from our data. But technically, we are subtracting off the value of the difference in proportions in the null hypothesis, and that's P1 minus P2. But we know that this is equal to 0 from the null hypothesis. That's what that suggests. P1 equal to P0 is just 0. So it's there, it's just a 0. Okay, so this whole thing is a test set. What you'll notice here is that we have a P hat without a subscript, and that is just the pooled sample proportion. Now the nice thing is your calculator does all this tedious calculations for you. Just like in the previous chapter we had 1 prop z-test, in this chapter we're going to use 2 prop z-tests. And it works very similar. You just have more inputs. In step 4 you still have a two-tailed test, left-tailed test, or right-tailed test. Again, you figure that out from the alternative hypothesis statement. Step 5 we're going to make a decision. And step 6, we're going to answer the question in the context of the problem using that same flowchart from before. But let's go ahead and just get straight into an example. Example 1. An economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. Okay, sounds like a claim to me. He obtains a random sample of 800 urban households and finds that 338 of them have internet access. He obtains a random sample of 750 rural households and finds that 292 of them have internet access. Test the economist's claim at a 5% level of significance. So of course we have to go through the conditions, right? The conditions are that these samples are obtained in a random method. Yeah, he does. N1 times P1 hat times 1 minus P1 hat. We'll come up with that pretty soon, all those values. So we'll have to test for that to see if this is greater than 10. And are the sample sizes less than 5% of the population? Well, if you just look at the numbers here, then we should be able to figure that out. So let's just go ahead and start describing what is going to be 1 and what is going to be 2. I'm just going to call urban 1. It doesn't matter, really, as long as you're consistent about it. I'll make rural 2. Okay, so X1, N1, and then P1 hat. Same thing for rural. All right, so for the urban households, 800 of them were sampled. How many of them have internet access? 338. And of course, if we divide those two numbers, we get 0.4225 exactly. For rural, we have 750 households, and 292 of those had internet access. Again, are these samples less than 5% of the population size? Yeah, I'm pretty sure 800 is less than 5% of all urban households, and same thing with rural. So yeah, that's checked off. It's just a second condition still needs to be met. So P2 hat is 292 over 750. We get about 0.3893 rounded. All right, let's see if this second condition is met. We have 800 times 0.4225 times 1 minus 0.4225. And we get something like, I'm just going to round. I don't really, this number doesn't have to be super accurate just because we're not using it in any further calculations. I get something like 195. And for sample 2, we have 750, 3893, 1 minus 0.38. We get about 178. Yeah, these are clearly greater than 10. So these both check off. So we can proceed with the problem here. One last thing I do want to mention is in the first condition, were these independently chosen? Yeah, there was no indication that households chosen in urban households had any dependency on what you chose in the rural households. Okay, if there was any, then there would not be independent, of course. All right, step 1. We have our hypothesis statements, null hypothesis alternative. And we are talking about proportions, right? And let's go ahead and identify that claim statement. That's the only way you can really get through this first step. At the very end, it says, test the economist's claim. What was his claim? At the very top, it says that the economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. All right, again, percentage is the key word there. That means we're talking about proportions. And of course, we're dealing with 2 different populations, urban and rural. All right, so the null hypothesis is always P1 is equal to P2. And we already know what 1 and 2 is. 1 is for urban and 2 is for rural. And this claim statement suggests that what? Well, it suggests that P1 is what? Greater than P2, right? Because urban is greater than rural. That is the claim statement. That matches the highlighted statement. Step 2, we have our significance level. It tells us that alpha is 0.05. Step 3 is our test stat. Now, of course, we have that ugly, complicated formula from the previous page. But what we were going to do is we were going to use 2-prop z-test, right? Because for proportions, we're always using a z. 2-prop z-test. All right, what are the inputs here? Well, you're going to have your sample proportion, which is x1 over n1, right? So we need those 2 values for both populations. And of course, I already have that listed above, so I can just recopy that. Well, so far, looking at the claim that P1 is greater than P2, if I just look at the sample proportions for P1 and P2, I get 0.4225 and 0.3893. So far, so good. But the whole purpose of doing this test is to see, are these significantly different? And of course, we always have to deal with the spread of your data. And if proportions have a distribution, then we're going to be able to figure out if these are significantly different. All right, let's go ahead and go over to the calculator. Okay, over here on the calculator, let's go to the stat menu. We're going to go to the same menu that we always go to, the test menu. And in this case, we're looking for 2-prop z-test. And I see it right there. It should be the 6th option. So I'm going to scroll down there, 2-prop z-test. Press enter, and we have all the inputs here, x1, n1, x2, n2, and then the alternative, and then we can calculate. So it's very simple. It's just a matter of knowing what the inputs are and being able to read this problem correctly and interpreting the answer. All right, in the null hypothesis, P1 was greater than P2, right? So we say it's P1, and then we have either not equal to, less than, or greater than. We're going to go to greater than. And let's go ahead and calculate. All right, we're going to have our z-score. I'm just going to use 2 decimal places. That's fine. Or at least 2. 1.33. I'll go with 3 decimal places. 1.329. And also we're going to pull out the p-value from here. The p-value is 0.09199. And of course, that's not less than our alpha. So we're not going to be able to reject the null hypothesis. We can already tell from this step. But we're going to go through all the steps here. And of course, it has other outputs here like P1 hat, P2 hat. We already calculated those. P hat with no subscript, that's just the pooled proportion if you needed that, which you probably don't. If you're already using this calculator to come up with this, you don't really need that. And then it just reiterates the sample sizes. So I do want to copy over the p-value for step 4, 0.0920. All right, that was a complete step 3. Step 4, we're going to draw a picture. How do we know what shape we're drawing? Is there a bell shape or skewed to the right? Well, your test stat always tells you that. Z-scores are always bell shape. The only thing that's not bell shape is your chi-squared, and later on we're going to talk about an F distribution, which is also skewed to the right. It looks very similar to a chi-square. So T's and Z's are bell shape. Chi-squares and F's are skewed to the right. We have a bell shape curve, symmetrical. is equal to 0 at the center. Let's go ahead and label our test stat. It's a positive value, so it's a way out here, 1.329. And what kind of tail test is this? Well, it's a right tail test because it literally points to the direction that we're going to shade. And what is that area of that shaded region? Well, it's already calculated for us. It's that p-value. Okay, that area is about 9.2%. And that seems to be a complete step 4. Step 5, we're going to make our decision. The decision is made by comparing the p-value to your significance level, 0.0920. Alpha is 0.05. Your p-value is greater than alpha. Again, what's the meaning of the significance level? It's the probability of committing a type 1 error. What's a type 1 error? It's if we reject the null hypothesis when in fact the null hypothesis is still true. We only want to make that error 5% of the time. If we reject the null hypothesis in this case, there's about a 9% chance that we make that mistake. We're only willing to make that mistake up to a 5% chance. So again, we're going to fail to reject the null hypothesis. In a sense, you're accepting the status quo to be true, that P1 is equal to P2 still. We don't have enough evidence to support our claim. And that's how we're going to come up with our conclusion statement, right? So we did not reject the null hypothesis. So in a sense, the null hypothesis is still true, right? That's still true. Therefore, we are not supporting the claim. And of course, the wording follows that logic. So let's go over to that flow chart again. All right, our claim was the alternative. So we're going down this way. Were we able to reject the null hypothesis? No. So the wording here is that there's not sufficient sample evidence to support the claim that, and in our case, the percentage of urban households with internet access is greater than the percentage of rural households with internet access. Okay, and here's the conclusion statement following that same template. What I'm underlining here again are the important keywords here, is not, and then the word support here. Again, that word support is used when the claim was the alternative, and the word rejection is used when the claim is the null hypothesis. So just like mentioned before, we can also do the same hypothesis test with a confidence interval. Let's see how that's done. Okay, so all the same conditions have to be met, just like before. And for a confidence interval for a difference between two proportions, that's what we have a lower bound and an upper bound that we need. Now your lower bound is this quantity. It's your point estimate minus your margin of error. And your upper bound would be that exact same point estimate, but in this case, plus the margin of error. Same thing, just like in the previous chapters. Now your calculator can come up with this interval using 2 prop z interval. And the inputs are just like for the hypothesis test, except for in this case, we have to enter the confidence level. Now, sometimes a problem will actually give you the confidence level that it's asking for. Sometimes you have to figure it out, and it might be based off the hypothesis test. If it's like a follow-up question, think of it like a step 7. Okay, and of course your output is going to have some sort of lower bound and some upper bound. And how does this test performed using a confidence interval? Well, again, if we have, for example, a two-tail test, so null hypothesis and an alternative hypothesis, you have P1 is equal to P2, and then you have P1 is not equal to P2. Of course, P1 equal to P2, this is the same as saying that there is no difference. Think of just using a little bit of algebra to subtract the P2 from both sides. You'll end up with P1 minus P2 is equal to 0. Now, if we get an interval that contains the 0, well, how can that be done? Well, let's draw a little picture here. Let's say we have our lower bound here and our upper bound here. And if 0 is somewhere around, let's just say it's like right here. Okay. Well, what do we know about the lower bound? It must have been what? A negative number. And what would you know about the upper bound? Well, if it's to the right of 0, it has to be a positive number, right? So if you have a lower bound that's negative and an upper bound that's positive, then you know that 0 is contained in that interval. So what do we conclude about that? Well, since we have a good confidence that your true difference is between that lower bound and that upper bound, and 0 is one of those possibilities, then we cannot say that there's a significant difference in the two proportions. Now, what if it doesn't contain the 0? Well, there's two ways that can happen. Okay, I'm going to draw two pictures. We have our lower bound, and we have our upper bound, and then we have another picture. We have a lower bound and an upper bound. So let's just say the 0 was right here. What does that tell us about the lower bound and the upper bound? Well, there must be two negative numbers, right? If they're both to the left of 0. So if both bounds are negative, then of course it doesn't contain 0. And of course, the 0 can be on the left-hand side here. And what does that tell us about the lower bound and upper bound? Well, that means they are both positive. Okay. So what we say about this, that there is a significant difference between the proportions, meaning if you're confident that your proportion's some negative number that doesn't contain 0, then you know that there's some pretty significant difference between these two proportions. And the same thing for the two positive bounds. So in this first case, we fail to reject the null hypothesis, right? We basically say that P1, the difference between P1 and P2 is quite possibly 0 because it wasn't outside of that interval. Okay, and in these two cases, we would reject the null hypothesis. We would reject that the difference is 0 because we were quite confident that 0 is not inside those intervals. All right, let's do an example. All right, example 2. This is the same example as before, but in this case, they're asking for a 99% confidence interval for the difference between the proportions of urban and rural households. All right, the conditions are the same as in example 1. Your best point estimate. Okay, so the best point estimate for the population difference, the difference between the population proportions, is your sample proportion, which is P1 hat minus P2 hat. Okay. And how's that calculated? Well, P1 hat minus P2 hat. Again, it is those two fractions. And you get 0.033 if you're rounding. If you just wanted the interval, you can just do all that on your calculator. It would just be 2 prop z interval. Of course, it's going to ask for all the inputs, your x1, n1, x2, n2, and so forth. And if you run that through 2 prop z interval, which let's go ahead and go over to the calculator to do that. Okay, we're here on the calculator. Let's go to stat. We go to test. And in the previous example, we dealt with 2 prop z test. Now in this case, we're going to do 2 prop z interval. So we have to find that. Should be option B. Okay. I still have the same inputs from the previous problem, so I don't have to add anything there. The confidence level in the problem, they said that it should be a 99%. So I'll just go ahead and put 0.99. And let's go ahead and calculate. All right, we get a lower bound of negative 0.0311 and an upper bound of 0.09741. Again, since one is negative and one is positive, then 0 is contained. So we can't say that there is a significant difference because since it's quite possible that 0 is the difference. So we can't reject the null hypothesis. So it's very similar to what we did before. So to come up with the confidence interval, it's P1 minus P2. This difference is anywhere between negative 0.0311 and 0.09741. And just as a bonus here, we can say the margin of error. If you remember from 2 chapters ago when we were dealing with confidence intervals, the margin of error is just the difference between your upper bound and your lower bound, which is just the range divided by 2, which in our case is 0.09741 minus a negative 0.0311 over 2. The opposite of a negative is a positive, so those two numbers actually add up. And we get something like 0.064 when rounding. And just to double check to see if that actually, if your point estimate, which is this guy here, and your margin of error does add and subtract to be these two bounds. So let's check that. We know that P1 minus P2 is your point estimate plus the margin of error. And on the left-hand side, it's a point estimate minus the margin of error. So this is just to check. Your point estimate is this guy, right? So that's 0.033. Margin of error is this thing right here. Same values here. And if you were to add those up and subtract those, you should get the same thing we got for the interval here. It's negative 0.031 and 0.097. And of course, I did round those numbers off, so it does match up. So how do we interpret this interval? Well, we are 99% confident that the difference between the proportion of urban households that have internet access and the proportion of rural households that have internet access is somewhere between negative 0.0311 and 0.09741. Now, since the confidence interval contains 0, we cannot conclude that the proportion of urban households with internet access is greater than the proportion of rural households with internet access, because it wasn't significantly different from 0. Okay, thanks for watching.